The water-based drilling fluid used to spud a well at the surface is engineered for shallow rock, but pump that exact same fluid to extreme depths and the resulting chemical failure will destroy the wellbore. These fluids exist as active chemical equilibriums, governed by specific applications, the surrounding geology, severe downhole contamination, and rising temperature. We track a fluid's evolution from a surface spud mud down to a 400-degree high-pressure reservoir. At specific thresholds, the baseline chemistry fails. Engineers must execute chemical conversions to maintain rheology and stabilize the rock. Miscalculating these transitions results in lost circulation, stuck pipe, or a total collapse of the wellbore. Reaching target depth is an exercise in applied crystallography, cation exchange, and polymer engineering. At the surface interval, the system begins as an unweighted clay-water mud. Engineers mix bentonite into water to achieve high rates of penetration through the first several thousand feet. Because the system lacks high-density weight materials like barite, it has a low buoyancy effect on the drilled cuttings. Hole cleaning depends entirely on the fluid's internal strength, its yield point, and plastic viscosity. As the bit drills, bentonite solids crowd the fluid, causing uncontrollable viscosity spikes. Engineers introduce lignosulfonate deflocculants, flooding the system with negative anions. These neutralize the positively charged clay, forcing the particles to repel one another. The flocks disperse, dropping viscosity back to optimal operating levels. While deflocculation manages surface solids, this highly dispersed state leaves the fluid defenseless against the chemically reactive formations found in the intermediate interval. As the bit reaches intermediate depths containing anhydrite or water-sensitive shales, the fluid is converted to a calcium-treated system to inhibit shale hydration. Native clay particles carry sodium cations, forming massive, swollen water envelopes. When introduced, high-energy calcium ions displace the sodium. This base exchange strips away the hydration layer, drastically shrinking the protective water envelope. Without this envelope, clay particles physically touch and clump into large flocks. This chart plots the effect of that clumping. As filtrate calcium increases in a high solid system, it creates a massive, sharp spike in viscosity, the breakover viscosity hump. To mitigate this risk, engineers mechanically reduce reactive solids, achieving a drastically flattened, safer viscosity curve. Achieving shale inhibition requires the mud engineer to intentionally destabilize and flocculate the fluid. The calcium breakover is a highly calculated operation on the rig. Further down, the wellbore often intersects younger shales. In these formations, calcium base exchange is too weak to stop the surrounding rock from hydrating and swelling into the hole. This requires a shift to potassium-based systems to achieve crystalline fixation inside the clay. Potassium's effectiveness relies on exact molecular dimensions. In swelling clays, the interlayer lattice gap measures exactly 2.80 angstroms. With a 2.66 angstrom diameter, the potassium ion slots precisely into that gap. This triggers the upper and lower clay lattice layers to physically snap together and lock. This internal ionic fixation is reinforced by an external physical barrier. Long synthetic chains of PHPA polymers are added to the fluid. Through encapsulation, these polymers wrap around the drill cuttings and the wellbore wall, preventing any remaining free water from entering the clay structure. But standard polymers degrade as temperatures rise. To maintain shale stability at higher temperatures, engineers introduce polyglycol systems. This system leverages the cloud point. As temperatures pass a threshold, polyglycol converts from soluble to insoluble. These insoluble droplets, or micelles, create a thermally activated mud emulsion. They physically jam into the filter cake's microscopic pores, completely sealing off fluid flow into the rock. Surviving reactive shales requires layering three distinct defenses: geometric crystalline locks, physical polymer wrapping, and thermally activated emulsion barriers. At the deepest stages of the wellbore, temperatures cross the 350-degree Fahrenheit threshold, entering the extreme high-temperature, high-pressure regime. Traditional water-based mechanics fail here. The organic bonds within the lignosulfonate deflocculants snap apart under the intense heat. High alkalinity and reactive bentonite clays will fuse together downhole, forming a rigid aluminosilica cement. Preventing this cementation requires a complete removal of reactive colloidal solids and native bentonite from the system. In their place, engineers deploy synthetic rheology. Advanced chrome-free synthetic polymers completely replace the viscosity and suspension functions of natural clays. These stabilizers manage low shear rate viscosity and fluid loss control reliably up to 450 degrees Fahrenheit without the risk of high temperature gelation. Reaching extreme thermodynamic depths requires the abandonment of native geology, relying entirely on synthetic molecular architecture to maintain fluid integrity. Achieving target depth requires a continuous sequence of engineered interventions designed to outpace the escalating hostility of the wellbore. At the surface, anionic charges disperse native solids. In intermediate sections, calcium base exchange shrinks clay-water envelopes. Against reactive shales, precise potassium geometry locks the clay lattice, and thermally activated polyglycol micelles seal permeable pores. Finally, at absolute limits, synthetic polymers prevent thermal cementation. True wellbore stability is achieved by mastering the molecular mechanics of the fluid at every inch of the descent.